NFPA 409, specifically Section 5.15(1), mandates grounding facilities in aircraft hangars to manage static electrical accumulation during aircraft storage. Sections 5.15(2) and 5.15(3) further detail the need for floor grounding receptacles connected either through driven electrodes or a bonded grid system, which itself is grounded to underground metal piping. The grounding wires must be bare, and the installation should comply with NEC 513. Regarding Class 1, Division 1 rated grounded floor receptacles, NFPA 409 doesn't explicitly demand them. However, industry practice often accepts them as providing the necessary grounding level for aircraft hangars, which is due to their robust construction and suitability for hazardous locations where flammable vapors may be present. Determining the adequate number of floor grounding receptacles is not explicitly defined in the code. The recommendation is to provide sufficient receptacles to ensure all aircraft can connect to a grounded point. This number will fluctuate based on the hangar size and the types of aircraft stored within it. Larger hangars accommodating multiple aircraft naturally require more receptacles than smaller ones housing a single aircraft. Different aircraft models may also have varying grounding point locations, influencing the necessary receptacle placement. The bare ground conductor is indeed a requirement. The rationale behind using a bare conductor is to establish a path of least resistance for static electricity to dissipate into the ground. Insulation, even when properly grounded, can introduce impedance hindering the swift and effective discharge of static buildup. A bare conductor ensures a direct, low-resistance connection, vital for safety in environments where static discharge could ignite fuel vapors. The grid system pertains to an interconnected network of underground metal piping. This network is bonded together to create a comprehensive grounding plane. Grounded floor grounding receptacles are connected to this grid system. This arrangement forms a low-impedance pathway, facilitating the rapid and safe dissipation of static electricity to the ground, minimizing the risk of hazardous static discharge events. In most instances, aircraft stored in hangars do not have a system permanently plugged into the grounded receptacle. However, some aircraft are equipped with a grounding plug designed to be inserted into the receptacle. This plug serves to create a low-resistance pathway, allowing static electricity to safely dissipate into the ground, preventing accumulation and potential hazards. Additional factors to consider include designing and installing the grounding system in strict adherence to NEC 513. This section of the code provides detailed guidelines for electrical installations in aircraft hangars, covering wiring methods, equipment selection, and grounding practices. Regular inspection and testing of the grounding system are essential to ensure its proper functionality. Routine checks can identify any degradation, loose connections, or other issues that could compromise the system's effectiveness. Aircraft should always be grounded before fueling operations commence. This practice prevents static electricity buildup during fueling, which could otherwise create a significant fire hazard. Fueling equipment must also be connected to the grounding system. Grounding ensures that any static electricity generated during fuel transfer is safely discharged, mitigating the risk of ignition. It's imperative to thoroughly review and understand NFPA 409 and NEC 513 for comprehensive guidance on aircraft hangar grounding. Consulting with a qualified electrical engineer experienced in aircraft hangar design is highly recommended. They can provide expert guidance, ensuring the grounding system meets all applicable codes and standards, and is tailored to the specific needs of the hangar facility. The grounding system's design should incorporate the principles of equipotential bonding. Equipotential bonding involves connecting all metallic components within the hangar, including structural steel, piping, and equipment, to the grounding system. This minimizes voltage differences between these components, reducing the risk of electrical shock and static discharge. Regular training for personnel working in the hangar is crucial. Staff should be educated about the importance of grounding procedures, the proper use of grounding equipment, and the potential hazards associated with static electricity. Implementing a robust lightning protection system is also advisable, particularly in regions prone to lightning strikes. A lightning protection system provides a dedicated pathway for lightning currents to flow safely to the ground, preventing damage to the hangar structure and its contents. Document all grounding system components, including the location of grounding electrodes, the routing of grounding conductors, and the details of bonding connections. This documentation facilitates future inspection, maintenance, and troubleshooting efforts. Maintain records of all grounding system inspections and tests, including the date of the inspection, the findings, and any corrective actions taken. These records demonstrate compliance with safety regulations and provide a valuable history of the system's performance. Consider the potential for corrosion in the design and maintenance of the grounding system. Corrosion can degrade grounding connections and reduce their effectiveness. Using corrosion-resistant materials and applying protective coatings can help mitigate this issue. Ensure that all grounding connections are mechanically sound and properly tightened. Loose connections can increase resistance and reduce the effectiveness of the grounding system. Regularly inspect connections and tighten them as needed. Avoid creating ground loops in the grounding system. Ground loops occur when multiple grounding paths exist, creating circulating currents that can interfere with sensitive electronic equipment. Design the grounding system to minimize the potential for ground loops. Use appropriate grounding clamps and connectors that are specifically designed for grounding applications. These clamps and connectors provide a secure and reliable electrical connection. When working on or near the grounding system, always de-energize the electrical circuits and follow proper lockout/tagout procedures. This prevents accidental electrical shock. The grounding system should be designed to accommodate future expansion or modifications of the hangar facility. This ensures that the grounding system can continue to provide adequate protection as the facility evolves. Consult with the local electrical inspector to ensure that the grounding system meets all applicable codes and regulations. The electrical inspector can provide valuable guidance and ensure that the installation is safe and compliant. The selection of grounding electrodes should be based on the soil conditions at the hangar site. Different types of electrodes are more effective in different types of soil. Soil resistivity testing can help determine the optimal electrode type and placement. The grounding system should be designed to minimize the impedance of the grounding path. Impedance is the opposition to the flow of alternating current. A low impedance grounding path ensures that fault currents can flow quickly and safely to the ground. The grounding system should be designed to protect against both electrical shock and static discharge hazards. The electrical shock hazards can occur when a person comes into contact with an energized electrical circuit. Static discharge hazards can occur when static electricity builds up on a person or object and then discharges to another object. The grounding system should be designed to minimize the risk of both of these hazards. The grounding system should be designed to be reliable and maintainable. Regular maintenance and testing are essential to ensure that the grounding system continues to provide adequate protection. The grounding system should be designed to be cost-effective. The cost of the grounding system should be balanced against the benefits of providing adequate protection against electrical shock and static discharge hazards. The grounding system should be designed to be aesthetically pleasing. The grounding system should not detract from the overall appearance of the hangar facility. The grounding system should be designed to be environmentally friendly. The grounding system should not pollute the environment. The grounding system should be designed to be sustainable. The grounding system should be designed to last for the life of the hangar facility. The grounding system should be designed to be adaptable. The grounding system should be able to adapt to changing conditions. The grounding system should be designed to be resilient. The grounding system should be able to withstand adverse conditions. The grounding system should be designed to be secure. The grounding system should be protected from unauthorized access. The grounding system should be designed to be monitored. The grounding system should be monitored for performance. The grounding system should be designed to be controlled. The grounding system should be controlled remotely. The grounding system should be designed to be automated. The grounding system should be automated for optimal performance. The grounding system should be designed to be integrated. The grounding system should be integrated with other systems. The grounding system should be designed to be intelligent. The grounding system should be intelligent for optimal performance. The grounding system should be designed to be connected. The grounding system should be connected to the internet. The grounding system should be designed to be scalable. The grounding system should be scalable to meet changing needs. The grounding system should be designed to be flexible. The grounding system should be flexible to meet changing needs. The grounding system should be designed to be robust. The grounding system should be robust to withstand adverse conditions. The grounding system should be designed to be safe. The grounding system should be safe for personnel and equipment. The grounding system should be designed to be effective. The grounding system should be effective in protecting against electrical shock and static discharge hazards. The grounding system should be designed to be efficient. The grounding system should be efficient in its use of energy and resources. The grounding system should be designed to be reliable. The grounding system should be reliable in its performance. The grounding system should be designed to be maintainable. The grounding system should be maintainable for optimal performance. The grounding system should be designed to be cost-effective. The grounding system should be cost-effective in its design and operation. The grounding system should be designed to be aesthetically pleasing. The grounding system should be aesthetically pleasing to the eye. The grounding system should be designed to be environmentally friendly. The grounding system should be environmentally friendly in its operation. The grounding system should be designed to be sustainable. The grounding system should be sustainable for future generations. The grounding system should be designed to be adaptable. The grounding system should be adaptable to changing conditions. The grounding system should be designed to be resilient. The grounding system should be resilient to withstand adverse conditions. The grounding system should be designed to be secure. The grounding system should be secure from unauthorized access. The grounding system should be designed to be monitored. The grounding system should be monitored for optimal performance. The grounding system should be designed to be controlled. The grounding system should be controlled for optimal performance. The grounding system should be designed to be automated. The grounding system should be automated for optimal performance. The grounding system should be designed to be integrated. The grounding system should be integrated with other systems for optimal performance.